Okay. Now I'm gonna go look at something for relativity. Um, I have to write down the meaning of relativity, right?
Well, just something to show that you've done some investigation on it. And it doesn't have to be that sophisticated. Um, Kind of like we talked about, you sort of go out to the internet here, you know, theory of relativity.
Because I'm checking Wikipedia right now.
Right. And that's a good place to go to just sort of like get a simple definition. It's uh
It's with gravity. That's obviously one thing. Um, it says it applies to the cosmological, but that's not explaining it basically.
yeah, so sometimes I go into images to see if I can find something that's a very simplistic explanation of it. And I truly don't really understand it, but you can think of time, fourth dimension is time. Um,
Mm-hmm.
but there's probably a better, like here. Um,
Relativity is based on two principles. Oh,
yeah.
okay. That works
I,
a little bit.
yeah, something like that could be okay, but I don't know how much they're going to.
How much they're asking for.
Yeah, yeah. But you want to give them something. That's there.
All right. Okay. I'm good for that. We can move
Okay.
on to like
Yeah. So what you can throw in. Yeah, it's up to you if you want to throw in whatever you have, will probably be fine. Now, we need a law in chemistry, so we need a chemistry law, and there's so many of them that we can look up here. Probably the um I don't know. I'm trying to find one that's kind of reasonable. How about the first law of thermodynamics? That's a good one. That's a pretty standard one. I know it does fall into chemistry. It basically says that, and you can see here, um, energy cannot be created or destroyed. Okay, so
got it.
energy cannot be created or destroyed, and it's okay to write it like this because it's a pure definition.
Okay. All right. Okay, I got that written
All right, so
down.
let's scroll down here. Well, we left off on 9. All right, can you read this out loud for us, please?
Yes. Janice has a genarium in a flower pot, and after a while it dies. Janice thinks, I wonder if it is because of the type of potting soil I used. So she goes to the store and buys a new ger
Geranium. Geranium.
geranium, oops, and a different type of potting soil to plant it. She also waters this new geranium every other
Geranium. Yep.
day and is careful not to forget about it like she did before. After the plant survives for 1 year, Janice decided that her experiment proved that this new brand of potting soil is excellent and recommends it to all her friends. Use the information in the link above and explain why Janice's experiment is not actually good enough to make the interpretation that she made. Help Janice out by designing an experiment for her, include all the steps of the scientific method, and inform on the link information on the link above. Be sure to specifically list all your variables and which type it is. Make sure the label from the experiment and the dependent variable and control variables. So basically, it's like we have to make a little bit of a hypothesis as well.
Yeah, and sometimes like the next question about this control group is uh is the answer to the previous one. So the reason this is a bad experiment is th there is no experiment. There's you need a, she is missing a control group, basically, which would be another potting soil.
Got it.
Like the same plant, uh, it would be the same geranium, but in another type of soil.
Mhm.
So the issue here, and you want to add a little bit more than this, but that is the core thing here. It's like if you just started watering another plant and it worked. We don't know.
And not to mention, she kind of cared about this plant a little bit more because, like,
You could
in a
exactly.
way,
He also
because,
watered
like,
the plant every other day. We don't know what
yeah,
she did before.
I'm gonna assume that she watered it every day. Some plants don't requiring a lot of watering, right? I
They
don't know. I
don't.
don't
You
think.
can overwater them.
Yeah, and that's another way you can kill a plant. 'Cause, I mean,
Okay.
this I
Yeah.
think personally, besides the fact that she used a different potting soil, I also kind of think that I don't think the soil did much. I think it's because ever since that plant, I should realize, okay, maybe I don't need to water it every single day. I think that's the biggest contributor, in my opinion.
Yes. Yes.
Yeah,
So help Janice out by designing an experiment for her. Include all steps of the scientific method and the information on the link above. Be sure to specifically list all variables and which type is. All right. So we're going to go back and grab these.
a lovely hypothesis.
Yes. We have to make another hypothesis. So this is where you can jump in and, you know, come up with those. Actually, I put them in the chat. Oh, that's the old chat. I won't have it in this one. So, all right, yeah, why don't you tell me your observation?
Okay. Well, the observation is Janice used a different type of soil, right?
Used a different soil, watered every other day, and the plant is still alive
Yeah.
after 1 year. Okay.
Yes. Okay. The question, let me think. I said it that the soil isn't the biggest contributor. Did the soil really help? Because I don't think it did.
Yeah, that's a good question. So the
Yeah.
hypothesis is that are you suggesting that's the water that's really better? And because I do think they're talking about soil.
Yes, but okay,
Because it
hold on.
says she wonders if it's because of the type of potting soil I used.
Yeah.
So the hypothesis is that the new soil really is better than the old soil, something like
Okay.
that. So what is your prediction?
Let me think this.
Like, what do you predict will happen when you use the new potting soil? We
When
get
I
all excited.
use when I use the new potting oil, sorry, potting soil, um, and I water it. Sorry, hold on, let me rephrase this. When I'm going to use Janice's name, when Janice uses the new potting soil and waters every other day, um, like I'm going to assume the soil is more it has more nutrients for the flower itself.
Okay, that's all great, but like, what's the prediction? Using a new potting soil will what? What will it do?
Will provide the flower with more nutrients.
Okay, so it will make the plant grow
Will
better,
make the plant grow.
grow better, something like that. I mean, it's not great, but that's okay. So the test here, this is where we really need to have a control group, which is
Mm-hmm.
the old potting soil, and the experimental group, which is the new potting soil. All right. And so our independent variable, why did it do all that? So our independent variable is the potting soil. That's what we're
Uh-huh.
changing. All right. The dependent variable is, and this is what we can measure, is the like the health of the plant. I don't know how we
Got
know
it.
that. You know, maybe it's how many times it flowers, something like that. All right. And so the control variable is how many times the plant is watered. It could also be like where the plant is positioned in the sun, or you know how much sunlight it gets.
Mm-hmm.
Now, what do we think the conclusion will be?
The conclusion will be um the new potting soil is better than the old one. Obviously,
Okay,
that's like
that seems reasonable,
simple and straight to the point
right? Keep it super simple. All right, good. So that is everything.
for lesson number one.
Yeah, I'll be right back with you. All right, so that takes care of that one. You said you sent over another thing for us to work
Lesson,
on.
yeah.
Okay. All right, let me go take a look. So is the plan to work on, oh, come on, really?
Oh no, what happened?
Is the plan to work on like one class per like day, or switch between them, or just as needed?
I think one class per day works just fine.
Okay. All right, so let me do the right thing here. I need to save some files before we proceed because so can you give me like what's the name of this class? Is this your
It
physical science?
Yes.
And is this like lecture one that we just did?
Yeah.
All right. All right. And then I'm going to figure out where to put this. It's not really lesson notes, but it's something. All right, I'll just put it there for now. All right, and so the second one is the physical science lecture two notes, or lecture two. Is that right?
Yes.
Or homework assignment two.
Well, yeah, but all of those names work, I think.
All right, put it in the wrong spot. Oh boy. Downloads. All right, so I will share my screen. Now, do they give you like a lecture to watch or any notes when you're doing this?
Yeah, they give me notes and some videos.
Okay, it would be, of course, excellent to watch those to some degree. The videos are probably easier than reading a bunch of stuff. All right, so base unit, base unit. Any idea what that means?
Um, no, not that I can think of.
All right, so a base unit is the like fundamental unit. These are my words. Fundamental unit for length, mass, and time. So there are others, but for length, it's and we're gonna do this. Length is typically in meters, mass is in kilograms, time is in seconds. So these are like the there and more. So there's like and more it more, and these are used to measure events in the natural world. It's like so that we know what we're talking about. Like you can't make up your own unit for length and expect people to accept it.
Got it. Okay.
All right, so now we've kind of answered the next one. What if the name and symbol use the base unit of length? So we already mentioned it's meter, and that's an M.
Mhm.
Mass is kilogram, km. Time is in seconds, S. Electric current is amperes, which is, I think, A. Thermodynamic temperature probably is Kelvin.
Kelvin?
Yeah, Kelvin. Yeah, which nobody uses, but that's what it is. Amount of substance is, I guess, a mole. Sorry, I have some formatting issues here.
No, it's okay. I've
Like
never heard of someone using Kelvin. Like, that's a name for a person for
it
science.
is. It is. A lot of things are named after the people.
I mean,
So this
that's
isn't a
true.
shock. You've got a planet named after you.
Oh, yeah, I do now.
So actually, it used to be that there was you could go you could go on the internet or call this phone number and they would name a star after you.
Really?
Yeah. You
I
could give it
assume
as
they
a
don't do
gift.
that anymore. I
I,
assume,
I think people realized it was a scam.
oh, yeah, kid me would do it though. If I was little, I would do it. I would do it.
Well, it sounds good. Hey, I named a star after you.
Yeah.
All right. Use the following examples. Do not do the same for prefixes centi, milli, and kilo. Okay. All right.
Isn't centi just centimeters?
Well, it could be, but it could refer to any unit. So what they're saying is the prefix centi means 100. Okay. There
Yeah.
are 100 100 centimeters in 1 meter. Okay. There are
Hmm.
10 There are 100 decig no centigrams in 1 gram. So this is a little bit weird, but the prefixes are deci is 10, centi is 100, milli is 1,000. So we're just going to replace this for the next one. So the prefix, let's see here. Milli means 1,000th.
Okay.
There are 1,000 millimeters in 1 meter. There are 1,000 milligrams in 1 gram. So it's like once you see it, I guess it's more clear. Okay, and then we have to do the one for kilo. So kilo is going the other way. Like there's this, that doesn't make much sense, but we'll just keep going here. Hopefully it makes. The prefix kilo means 1,000. There are 1,000 grams in 1 kilogram.
Mm-hmm.
There are, oh, this is kilometers. Whoops. Oops. Went the wrong way. There are 1,000 meters in 1 kilometer. Did you ever go to a school where they had a track? Have you ever
Oh
been to a
yeah.
track? So if you go around the
Yes.
track once, that's 250 meters. No, sorry,
Uh-huh.
no, that's not true. It's 400 meters if you go around the track. Just to give you an idea. So if you go around the track 4 times, that's 1,600 meters or 1 mile,
Oh
roughly.
wow. Is this kind of like the way how they can convert miles to kilometers and or
Yes,
something? Yeah.
exactly.
Because when you go to Europe, you use kilometers.
Yeah. And in Canada, I think uses kilometers. In certain
Oh
parts of the
yeah, that
US,
too.
when you get close to the border, you might see kilometers. Okay. Um, why don't you look up what a derived unit is and see if you can tell me what, kind of look that up in your own words. It'll be a straightforward thing on the internet. Nothing.
A very straightforward thing on the internet.
I hope so.
A derived unit is a unit that results from a mathematical combination of base units.
There you go. So it's a combination of base units.
Okay.
All right. That's it. I mean, there's not much more that's needed. So for area is a length times a length. So that's a meter times a meter, not an
Mm-hmm.
M&M, a meter times a meter, which is a meter squared.
Got it.
Density is a mass per unit volume. Okay. So your mass would be a kilogram per something. However, they typically don't use kilograms for density. It's usually grams per centimeter cube. Don't know why, but that is what it typically is.
Got it. That was
Okay.
a big question, and it still is big.
Yeah, we're still going here. Still going here.
Question number two, because this is all math.
All right, convert. So this is where you got some math. Um,
Yep, this is the math that I was expecting with converting everything to degrees.
yeah, and there's a few other things here. Um,
This is the degrees in Fahrenheit math is what my parents are likely they've been trying to tell me because, when you go to other places around the world, they don't use Fahrenheit. They use Celsius.
yeah, so the first thing here is that to go temperature in Kelvin, TK is temperature in Kelvin, is the temperature in Celsius plus 273. Okay, so your first calculation here is that the temperature in Kelvin is 50 degrees plus 373, 273. It's 323 degrees Kelvin. Is that okay?
Yes.
The one to go from C to F is a bit more complicated. Let me pull up the formulas here. Did you get like a formula sheet in this class?
Let me see. I hope so. No, there likely is a formula sheet because, like, if they didn't give me one, how is that gonna help?
Well, maybe it's in the lesson notes. True, of course.
Yeah.
Celsius to Fahrenheit, Fahrenheit to Celsius. Okay. So here are the formulas that we might need. Okay. Just throw them in the notes here in case you need them later on.
All
So
right.
to go to Fahrenheit, temperature in Fahrenheit is the is 1.8 times the temperature in Celsius plus 32. So so in your problem, the temperature in Fahrenheit is 1.8 times 50 plus 32. You have a calculator available?
Yep. Does the what's it called? What's the calculator you kept wanting me to use?
A Desmos Scientific?
Yeah. Does will it work for this or do I have to use
Of
something
course. Yeah,
else?
of course. Of course.
Okay, I haven't used Desmos in a while, so I hope that I'm no longer rusty.
I think you'll be okay.
I think I'll be okay too. Desmos, where are you? Scientific. It's like once you're on Desmos, you can't turn back. It's like part of you, man. Do I also have to include the T
Just the
the
part that's highlighted here, 1.8 times 50 plus 32.
Okay, that's 122.
122 degrees Fahrenheit.
Sounds like Arizona.
Yes. Yes. So cool summer day. All right. The
Very cool.
yeah. The next one here is to convert to Celsius and Kelvin. So the temperature in Celsius is 5/9 times the temperature in Fahrenheit minus 32 degrees. Okay, so I'm just using the formulas here in this picture. The temperature in Celsius is 5/9 times 120 degrees minus 32. So will you calculate that in Desmos for us, please?
Yes, I will. Okay, I got 48.8.
Okay,
Is that right?
yeah, that's right. 48.8 degrees Celsius. Okay, so now we're going to convert to Kelvin. So the temperature Kelvin is the temperature in Celsius plus 273. So you just take the number you just found, 48.4, and add it to 273.
All right, and let me go figure out what that is. That's like 321.4.
Okay.
That's
Yeah,
a
tutoring.
that's that's a scorching.
Well, again, Kelvin is not the same as what we're used to, so you gotta keep that in mind here. Um, so now we're on to the last one here. So temperature Kelvin equals temperature Celsius plus 273. So to get the temperature in Celsius, we take the temperature in Kelvin and subtract 273 degrees from it. So you're given the temperature in Kelvin, and you're going to subtract 273 to get
Okay.
the temperature in Celsius.
That's hold on, I accidentally typed it in wrong. That's 77 degrees.
Celsius. All right, now to get the temperature in Fahrenheit, you take, and I'm going to go back and look at the formula. You take 1.8 times the temperature in Celsius and add 32 to it. So it's 1.8 times 77 plus 32.
That's 170 degrees. 0.6.
All right.
I love the fact that they're giving us these degrees. This just proves that if you live in the desert, you're burning a lot,
That is true. That is true.
which is
Okay.
me right now.
It's warm. It's getting a little cooler. A little,
Yep, just
the,
just give me another month and then I will be warm and toasty.
all right. So question three here, it says express the following numbers in correct scientific notation. This one, do you remember how to convert these or not? Something you would have seen in a previous math class.
If it was in a previous math class, I feel like I've seen them. I think I've
Okay.
done this in seventh grade, but I don't remember it at all.
So the decimal point is there, and we need to move the decimal point so that it's 7.61. See where the decimal point is there? How many times do you move the decimal to the left? So you just count 1, 2, 3, 4.
Okay.
So the rule here is that moving the decimal left is a positive exponent.
Mm-hmm.
The base is a number between 1 and 10. Uh, so 1 inclusive, 10 exclusive. So basically it can't be 10, but it could be right up to 10. So it could be like 9.9999999, so on. All right. So let's do number 3 because 3 is more like number 1. See where the decimal is? It's over here to the right at 2.
Yeah.
How many times are you moving the decimal to get it to 5.62?
Um, 5.62. Two times.
2 times. So that is your exponent. All right, so let's do the same thing for this one. It's 7.812 times 10 to the And then again, your decimal is here.
So you would have to move it, 7 times?
Yes, looks right. So for
Damn,
the
that feels
other
so smart.
ones, it's going the other direction. So when you're moving the decimal to the right
It's
is
negative.
a negative
Oh,
exponent. Yeah. So you gotta figure out how many times you're moving to the right. So this one is 6.74 times 10 to the, and you just have to count how many times to the right you're moving the decimal.
6 times. Well, -6 times actually.
Yeah, -6. All right. And then the same thing down here for this last one. This is 2.12 times 10 to what power?
-3.
Yes. Right.
Yay.
Got that all down. So now this one's going in reverse. It's kind
Ooh.
of the reverse instruction. So a positive exponent means moving the decimal right.
Okay.
So this is 287. Okay, so I've moved the decimal to the right 2 times, and I've got to go 9 more. So 1, 2, do it differently. So see, the decimal was here, right? 2.87, but if I move it right 2 times, now I'm going to start adding zeros. So moved it 2 times. So 3, 4, 5, 6, 7, 8, 9. There's your decimal. And then you add commas to make the number more readable.
Mm-hmm. That is a lot of numbers. Okay. So
Let's try, why don't you try number 7 on your own? Basically the same thing.
okay. Okay, I can use the Desmo Scientific for this, right?
Sure, but you're just moving the decimal to the right 5 times. That's what that 5 means.
Okay, so it would be like um okay, it would be so it'd be like so I got like I'm gonna just type it in there because I don't know how to say it
Yeah,
exactly.
that's fine. Yeah, that's what the chat is great for. Copy and paste.
Yeah, that's wait, I'm missing a 3. There we go. That's how much the decimal moved.
All right, yeah, so 1, 3, 3. We good. All right, looks good to me. So now a negative exponent. That's not what I wanted. A negative exponent moves the decimal left.
Okay.
So it was 8.04. So now we're gonna go left. So now it's there. That's one time. And then we're gonna add some zeros in. So that's 1, 2, 3, 4, 5.
Okay. So I gotta move it to the right. So that would be
But try number 9 on your own here. Again, you can use the Decimus if you want.
okay. So for number nine, it'd be like 0.03441.
Perfect. Try number 10. It's the same thing. And
Oh,
there's
that's a
no
lot of
work. Like, yeah, there's no
that's a
work.
lot of
You just,
zeros.
yeah, type it in there if you want.
And not to mention there's two decimal points in there. Can you scroll back up, by the way, please?
Sure.
Thank you.
Sorry, I was looking at the next questions we're gonna do.
No, you're fine. Um, did I type this in wrong? Let's see. 6.9 times 10 to the power of -8. I type that in, but then it doesn't give me like a decimal point. It just gives me 6.9 times 10 equals negative, like 10 to the power of -8.
But that's why
That's it.
you've got to be able to do it, on your own
Yeah.
here. Like that's moving it once, and then you start counting 2, 3, 4, 5, 6, 7, 8,
No,
like
I'm gonna
that.
just do it on a piece of paper real quick.
Yeah,
I think I got the answer. 1 second, let me just type it in. I think this is right.
so I'll just copy and paste and compare to what I wrote here. The 0 there. Yep, exactly the same.
Yay.
All right. So we've got some more questions here to answer that we're not going to have time for today. 6 you can maybe do on your own. It refers to this article. 7 you have to do on your own. You have to go around and measure something like around your house. So, like choose small things. And I would just things in the kitchen. Or yeah, I mean keep it simple. You know, things in the
Okay.
kitchen. They tend to be small. A fork, a knife, a can, a bowl. Okay, something like that. So give that a try for next time. We're going to go ahead and stop here for today.